You hear words like RAG, tokens, LLM, models, and it feels very confusing to you. Today, we will understand all of these AI concepts in the easiest and simplest way possible. I'm Gagan, your host. The purpose of this video is to set strong intuition so you understand these concepts and can follow along in the series. Let's start with what is AI engineering. AI engineering is basically building applications using big ready-made AI models. We call them foundation models. As an AI engineer, you usually start from off-the-shelf models, often via APIs. Adopt them with prompting, fine-tuning, RAG, and other techniques, and deploy them so people can actually use your app. And you are not just playing with the models. During deployment, you also make sure you are evaluating and monitoring the models. You know which model is better for which purpose. You follow the security and cost controls, and also you are responsible for performance and speed. Let's understand the difference between AI engineering and ML engineering. ML engineers focus on creating and improving the models themselves. They work with data, train models, tweak architectures, optimize accuracy, etc. AI engineers often focus on using those models to build applications and products. The foundation model is a huge model which is trained over tons of data, which can be text, images, videos, etc. You can adapt it for a variety of tasks like text, images, videos, sometimes all together. As the word says, foundation, it is very powerful model, but it is incomplete until you adopt it for a specific task, like building a chatbot, summarizer, code assistant, video generation. LLMs are a type of foundation model. They are trained to predict the next text. A LLM is a foundation model that is actually focused on language. They are trained over a large amount of text and code. So that's why LLMs are very good at chatting, answering questions, summarizing code, summarizing text, and a lot of things related to text. They don't actually look up the data from database. They encode knowledge in their parameters, and they use that parameters to generate the likely text. So they can be right, but they can also be confidently wrong. So that's what we call hallucination. Let's now talk about transformers. We have had text models for a long time, but the reason modern LLMs are so powerful is thanks to the change in design, the transformer architecture. Transformers allow training to happen in parallel, which is much faster, making it practical to build the large language models we use today. The key innovation here in the transformer architecture is attention mechanism. Look at this sentence. The server was restarted after it stopped responding. To understand this, the model needs to know that it refers to server, not the restart action. Attention allows the model to focus on word server while processing the word it. We use multi-head attention, which means different heads focus on different things. One might track grammar, another tracks tone, and another tracks relationships across parameters. Now we need to know how models learn. When we say a model is learning, we mean it's updating its parameters. These are internal numbers learned during training to minimize mistakes. More parameters generally mean it can capture more patterns, but it also costs more to run. Then we have hyperparameters. These are the settings we set, like knobs on a machine or configuration settings on a machine to control the output after the model is already trained. The most important hyperparameter you will use is temperature. Think of it as a creativity deal. Low temperature makes the model safe and predictable. It's great for facts. High temperature makes it creative and surprising, perfect for brainstorm. We also have top K, where the model only picks from the top 5 or 10 guesses depending upon our configuration. And top B, which builds a pool of likely candidates until it hits a confidence threshold. Together, these control balance consistency and creativity. Another important topics are tokens and context. Models don't think in a whole words, they think in tokens. A token can be a word, part of word, or just punctuation. Context is like the model's working memory. It includes your conversation so far, your prompts, and the answers it's generating. Every model has a limit. If you exceed it, the model forgets the oldest parts to make room for new tokens. That's called context window. Now it's time for prompt engineering. It just means writing good instructions. We can tell the model what role to play, what format to use, and what rules to follow. There are two types of prompts: system prompt and user prompt. System prompts, like you are a professional email writer, and a user prompt, like write an email declining this meeting. You can use zero shot, like no examples within the prompt, or few shot, giving it a few examples to copy. This is called in context learning. You aren't changing the model permanently, you are just teaching it for the specific conversation. When you want permanent behavior changes, you use fine-tune. This means retraining the model on your own data so it learns a specific tone or a domain. Full fine-tuning is expensive, so we often use PEFT technique, parameter efficient fine-tuning. Think of it like this. Instead of rewriting a whole book, you just add a sticky note with the new information. LoRA is the most famous technique for this. Now let's move forward to how to make the models practical. To make models faster and smaller, we use quantization. It's like compressing high-resolution photo. You store the numbers with fewer bits to save space while trying to keep the high quality. We also use distillation, where a small student model learns to copy a large teacher model. Finally, there is preference fine-tuning. This is where humans rate answers, teaching the model to be helpful, safe, and polite. This is what makes a raw model actually usable for chat. Even the big models don't know everything. They don't have recent information or information about your private data. To fix this, we use RAG. We feed the model by retrieving data from your database, and we store them as embedding. Embedding means we convert the documents into the form of numbers. Embeddings turn text into list of numbers, which are called vectors. Words with similar meanings like car and automobile end up close together in the vector space, which make them easier to find. Let's now understand chunking and ranking. Before searching, we split documents into chunks. If chunks are too big, you get irrelevant info. Too small, if these are too small, and you will lose context. After finding chunks, we use ranking to order them, ensuring the very best evidence goes to the model first. Under the hood, we have encoders and decoders. An encoder takes raw text and turns it into numbers, which are embeddings, great for understanding and search. A decoder takes those numbers and predicts the next word, which is great for generating text. Some models do both, but LLMs are mostly decoders. So far, we have talked about LLMs and chat, but an agent is an AI that can plan steps and take actions as well. Agents use tools. The model doesn't run the code itself. It just says, I want to call the search tool for something like weather in Chandigarh. Your code runs the tool, gets the result, and gives it back to the model to finish the answer. Now, another important topic is inference. Inference is the moment you actually use the model to generate an answer. Next is evaluation. How do we know if a model is good? We use benchmarks, standardized tests for math, coding, and safety depending upon our scenario. We use metrics like perplexity or ROG, which are helpful for evaluation. A popular modern trick is LLM as a judge, where we use a smart model like GPT-4 to grade the answers of a smaller model. The last topic for today's video is MCP, Model Context Protocol. Finally, as systems grow, we need a standard way for models and tools to talk. MCP is like a universal adapter. Instead of custom coding every integration, you plug tools into MCP and everything works together cleanly. Let's wrap up today's video. That's the big picture of modern AI engineering. We have covered the foundation models, transformers, RAG, embeddings, and AI agent and MCPs. In the upcoming videos, we will just start with hands-on practical exercises. Thanks for learning with me. I'll see you in the next video.